This video is about thermal conductivity. We'll begin by learning thermal conductivity basics, along with the related formula, and then we'll work through a thermal conductivity example. Let's see the basics. Earlier, we learned about thermal conduction, and saw that, for example, most metals are good conductors, while glass and some plastics are poor conductors. When we heat one end of a metal rod, after some time the other end of the rod also heats up. During this process, energy is transferred, or in other words conducted, through the rod. The quantity known as thermal conductivity allows us to quantify how well a conductor is able to transfer energy. So one way we can define thermal conductivity is that it is the measure of a thermal conductor's ability to transfer energy when in the steady state. We can say that a conductor is in the steady state when the temperature at any point in the conductor remains unchanged over time. Let's move on to unpack these definitions and then see how we get the formula that includes thermal conductivity. Imagine that we have a thermal conductor that looks like this. It could be, for example, a metal block. We'll assume that the temperature at the left end of the conductor is T1 and at the right end it is T2. We'll also assume that T1 is larger than T2, which means that energy flows through the conductor from left to right. For our purposes here, we'll also suppose that the conductor is in a steady state, so T1 and T2 remain unchanged during a certain period of time. Let's say that in this time, a delta Q amount of energy is transferred through the conductor. Note here that since the conductor is in the steady state, in other words, there is no temperature change within the conductor, the same amount of energy enters and leaves the conductor. Finally, we'll denote the cross-sectional area of the conductor as A and its length as delta X. Having clarified these details, now we are ready to develop the formula that is provided in your data booklet and that includes thermal conductivity. Let's see the different variables in this formula. On the left-hand side, we have the rate of energy transfer through the conductor, so delta Q over delta T. Here, delta T is the time during which delta Q is transferred through the conductor. Another way to think about delta Q over delta T is that it is the power input to the conductor. On the right-hand side, we have the thermal conductivity of the conductor, denoted by lowercase k, multiplied by the cross-sectional area, times delta T over delta X. Here delta T is T1 minus T2, and delta T over delta X is called the temperature gradient across the conductor. Let's summarize these variables in a table. Rearranging the equation, we can express K, so thermal conductivity, and we get that it is equal to delta Q over delta T, so the rate of energy transfer through the conductor, divided by the cross-sectional area, and by the temperature gradient, so by delta uppercase T over delta X. We are now ready to move on and work through a thermal conductivity example. In our example, we are asked to estimate the thermal conductivity of iron, so in the formula that we just learned, we are looking for K. Let's assume that the block is positioned like this. Adding the dimensions, we can write 5 centimeters here, 10 centimeters here, and 25 centimeters here. As for the temperatures, we'll assume that the left end of the block is at 20 degrees Celsius, and that its right end is at negative 10 degrees Celsius. Let's stop here for a moment to note that the position of the block does make a difference to our final answer, in the sense that if we would assume that the temperature difference is along the 5 centimeter or the 10 centimeter edge, we would get different values for K. We are given the power supplied to the block. On the left-hand side of our formula, we have delta Q over delta T, so energy transferred over time, which is equivalent to power supplied. Let's substitute. Doing so, we get that 50 is equal to K times the cross-sectional area, and here I will work in meters, writing 0.1 times 0.05. Delta T, so the temperature difference, is 30, and as this is a temperature difference, it has the same value in degrees Celsius and in Kelvin. Delta X, so the length of the conductor, is 25 centimeters, so 0.25 meter, so here we get 30 divided by 0.25. Solving for K and rounding to two significant figures, we get about 83. Before wrapping up this video, let's take a moment to think about the unit of thermal conductivity. In our substituted formula, power on the left-hand side is in watts. On the right-hand side, 0.1 times 0.05 is an area, so its unit is meter squared. 30 is a temperature, so its SI unit is the Kelvin. And 0.25 is a length, so it is in meters. Rearranging, we get that the unit of thermal conductivity is watts per meter per Kelvin. Keep in mind that thermal conductivity is specific to a given substance or material, so good thermal conductors have a high thermal conductivity value, while poor thermal conductors, in other words thermal insulators, have low thermal conductivity values. For example, the thermal conductivity value for copper, a very good thermal conductor, is 400 watts per meter per Kelvin. However, the thermal conductivity value for air, which is an excellent insulator, is about 0.026 watt per meter per Kelvin. So with this, we have completed our learning about thermal conductivity.